Shall we get started? What do you think? I think we waited long enough, like 7 minutes. Probably the latency between that room and this room is not 7 minutes. Depends on how fast you walk, of course, but I think I could do it much faster. Okay, well, hopefully you're here for the seminar course in computer architecture. I see some familiar faces. That's good. It's good that you're back for this course. Maybe we can go through these relatively quickly since you already... How many people have taken my course? Okay, is it everyone? Oh, maybe not everyone. Okay, so we'll go through some of it still. Maybe I'll go through some of this fast. But basically this lecture is more motivational, and also we're going to cover what we're going to cover in the rest of the semester. And then next lecture, or next meeting I should say, it's not going to be a lecture, but it's going to be an example of a presentation that we expect you to deliver. So hopefully it'll be fun. You can already find that presentation online from last year, so it's going to be similar to that. But maybe we'll cover a different paper. So hopefully you're here to study computer architecture, right? Okay, so I'll motivate you a little bit more based on what we've discussed in Digitech last time. Actually, we changed the title of Digitech from Design of Digital Circuits to Digital Design and Computer Architecture to more accurately reflect what we've covered. Because digital circuits is a very broad name, clearly, right? But digital design and computer architecture more accurately reflects what you have covered when you took the course. But as you probably know by now, computer architecture is a science and art of designing computing platforms. And this is a more general definition. We'll have a somewhat more specific one later. Especially today, because we're really doing platform design all the way from algorithm to architecture as hardware. It spans hardware, the interface between the hardware and the software and system software, and the programming model itself. So if you remember from Digitech, we covered GPUs, and they have some certain programming model, right? It's coupled with the architecture itself. It could have a different programming model, clearly, but there are programming models that better fit different kinds of architectures. And it's good to think about an entire system that way as the computer architecture itself. Of course, the goal is to achieve a set of design goals in the end. And these could be many different design goals depending on what you're designing. For example, if you're designing a supercomputer or a specialized accelerator, it could be the highest performance on Earth on workloads XYZ, right? Where you can fill in your favorite workloads. It could be machine learning. But then machine learning is also very general, right? There are many specific classes of different types of machine learning. A lot of the algorithms that are being designed right now as machine learning accelerators, they're more neural network accelerators or deep neural network accelerators. They don't necessarily work well for other types of machine learning algorithms like reinforcement learning, right? Okay, but these you normally design architectures for some sort of design with some design goal in mind. I usually have a set of design goals, not just one single goal, right? Highest performance on Earth may be the most important design goal, but there may be cost constraints, there may be energy or power constraints and area constraints as well, right? This could be another design goal, right? Longest battery life at a form factor that fits in your pocket with cost less than some francs. Clearly now you can specify more sophisticated design goals this way. Or it could be, so these are, this one is very special purpose, of course, right? And I think of like accelerators as more special purpose. Even supercomputers are relatively special purpose, right? If you're designing a huge supercomputer, you're really more special purpose on some workloads, usually scientific workloads. Yet it's a very different special purpose design. But if you look over here, this is a more general purpose design goal. You get the best average performance across all known workloads or workloads you care about at the best performance cost ratio. Right? This is more general purpose design. If you think of Intel and AMD and their mainstream processors, they try to optimize for this. So clearly this is a very different design goal than this one and this one over here. So it's good to keep this in mind clearly. And there could be many, many other design goals. And clearly designing a supercomputer is different from designing a smartphone, but many fundamental principles are similar as you have seen in Digitech, right? Okay, and this was one of the definitions we used in that course. It's computer architecture is the science and art of designing, selecting and interconnecting hardware components and designing the hardware-software interface to create a computing system that meets functional, performance, energy consumption, costs, reliability, and other goals. This is more limited, I would say. It doesn't cover, for example, the programming model. But going forward, I think computer architecture is expanding because we're really specializing for the algorithms and the applications. Okay. So hopefully you're familiar with all of this, right? Okay, we can go faster. And I've shown you this picture also before at Digitech. This is Moore's law. So an enabler of computer architectures has been Moore's law. By the way, before I move over here, I keep saying science and art. And you remember the discussion from Digitech. It cannot be an exact science, like physics, for example, because we're really designing something for the future. And if you're designing something for the future, that thing will be used 10 years down the road. And it's very hard to scientifically figure out what is the best thing that you're going to design. Even if you know your requirements extremely well, even then it's very hard to figure out scientifically exactly what is the best thing that you're going to design would be to satisfy those requirements, because then you need to model everything that's going to happen between now and 8 years down the road, right, or 10 years down the road. Theoretically it could be possible, but practically we don't know a way of doing that in science today, because we don't know how to predict the future. And in the future, workloads change, people change, and usually you're not designing something that fits the demands of the user and the workload 5 years down the road perfectly. That's why there's a lot of art involved in computer architecture, just like building architecture, as we've discussed in Digitech also. Okay, so Moore's law has been an enabler. This is actually interesting. This is 2005, and last time Moore's law essentially says that component counts that you can cram into a device doubles every other year. Okay, double, give or take. It increases basically. People argue that it's slowing down or not slowing down. Anyway, we're not going to go into that, but this is the original paper. How many of you have read that paper? Okay, because that was an assignment actually, right? When some of you took the course, not all of you perhaps. Well, optional assignment. So basically this is what Moore plotted. This is an empirical law, basically plotted you can see that the number of components per integrated function, devices, essentially in an integrated circuit, and he showed that it's doubling every other year or so. And he projected that this will continue, but this is another look at the law itself. This is the number of components per integrated circuit on the x-axis and the relative manufacturing cost per component. And he speculated that there's a minimum when you draw the curve at a given year, and that minimum shifts down as you go, as the technology scales basically, as your manufacturing capability becomes better. And that's what the enabler is, basically reducing the cost of integrating more components in a circuit. And that's why it's scaling. So people are speculating a lot these days that Moore's law has already ended or is ending. As long as this curve shifts, it's not ending, basically. The key question you should probably ask to someone who says Moore's law has ended is this curve still going this way? Right? And I'm not sure if people have really plotted it, but clearly people are making economic decisions right now based on the fact that the curve is shifting. And I'll give you some examples in a little bit. Okay, so this is 2011 actually. If you look over here, this is at 2.6 billion transistors on a given chip. But we're much higher actually today. Today we're in 2019. So I believe this Moore's law is continuing. It's becoming difficult to integrate more components in a single chip because of various reasons. Reliability becomes a problem, and making clearly there are manufacturing difficulties also. So making those chips become more and more costly. But people are actually pushing to make sure that they're actually able to make it. So we're at 7 nanometers today in terms of feature size, and I believe that's going to go down, although it's going to become probably more difficult. And you can fit this curve over here also, as you can see. It's kind of nice to play these games. Okay, if you haven't read it, I recommend reading it. It's not going to be a required reading for this course, but it's only 3 pages. And this paper that was published in 1965 actually covers a lot of interesting things. You can see by 1975, Moore says economics may dictate squeezing as many as 65,000 components on a single silicon chip. I will show you in a little bit that we're much higher today, as you can see, right? And that has enabled a lot of innovation in computer architecture and in workloads also, because we can integrate many things on a single chip or a single wafer, as we will see. We can enable many more things. But of course, this comes at a cost, right? It's not for free. There's nothing for free in design. It's always a trade-off. As you keep adding more components, you generate more heat because these components will be switching potentially concurrently at the same time. And then he also asked the question in that paper, will it be possible to remove the heat generated by tens of thousands of components in a single silicon chip? Today we'll have billions of components. Right? And heat removal is still a problem, of course, right? Okay, so why study computer architecture? Moore's law is an enabler to put more stuff on a single chip. And that enables bigger systems and better systems, no question about that. But at the higher level, we want to enable better systems. We want to make computers faster, cheaper, smaller, more reliable, because we have use cases for them. And even if you may not imagine what the use case may be for a faster computer, someone else will find it. There's no, and this has always been proven over decades and decades. People sometimes question, why do we need faster computers? And someone builds a faster computer and someone figures out how to use that faster computer. No question about that. They could use it for good or for bad. Technology is agnostic to ethics, right? Any technology can be used for good or bad. In the end, people use it for good or bad. Enabling new applications. Well, I guess I already said this basically. You exploit advanced and change in underlying technology and circuits to enable better systems. And also you exploit changes in design, right? Creativity. I should probably add creativity somewhere over here. You enable new applications, as we've discussed. Somebody will make use of the speed or the efficiency. Like 20 years ago, maybe we didn't imagine life like 3D visualization, but today these are actually within reach. Maybe virtual reality is not completely within reach right now, but people actually made a lot of progress in that as well. And you can see there are other applications that are coming, as we may touch on in a little bit. And we can enable better solutions to problems also, because a lot of innovation is really built on trends and changes in computer architecture, especially today, because we're very much constrained in terms of performance and energy by computer architectures that we can build for a given application. Okay, and also, of course, on top of all of this, we want to understand why computers work the way they do, so that we can fix issues we may have with them, or we can fix issues we may have with the current design, so that we don't repeat the mistakes for the future, right? Okay, so I think I already said this in Digitech at some point, but today I think is a very exciting time to study computer architecture, because many things are changing, and industry is in a large paradigm shift to new architectures. There are many different potential system designs possible. And there are many difficult problems. We're going to cover some of these problems in the papers that are going to be presented and discussed. And this is really a seminar course, so this is going to be the only lecture, maybe the next one. But in the next one I would like some discussion also. But this is really going to be the only lecture that you will have. We will have discussions and the rest. We will present papers that are covering a lot of these interesting problems. So many difficult problems motivate and caused, they're also caused by this paradigm shift, because there are difficulties we have at different levels. For example, workloads pose a lot of difficulties. We're hungry for data and new applications. Power, energy, and thermal constraints, as Moore envisioned, those are important. Complexity of design has caused a lot of problems. Difficulties in technology scaling has caused a lot of issues. And you remember RowHammer from Digitech, for those who've taken the course. That's an example of a difficulty in technology scaling leading to a reliability problem which can be exploited as a security vulnerability. We'll briefly talk about that. Also memory problems, we'll focus a lot on memory for sure. Reliability problems, programmability problems, and security and privacy issues. These are all within the domain of what we're going to cover. And you're going to select some papers that each of you is going to present to the group, and we're going to have a discussion. So we're going to critically analyze papers, as we will see. And clearly there is no clear or definitive answers in the general sense to these problems, because these are very practical problems, and you may have solutions in some areas, but you may not be able to completely solve all of these problems in the general sense. So we're not doing theory here. In theory, you can prove theorems, right? But here, it's going to be very difficult to prove anything in this system. Okay, so I think these problems affect all parts of the computing system, computing stack. Basically, if you do not change the way we design the system. So you remember this picture that I showed you earlier also, well, in the previous classes. Basically, we have problems and they need to be solved by electrons, and we have a stack, essentially the levels of transformation to enable the solution of the problems by the electrons. I'm not going to go through this, and user clearly interacts with multiple parts of this, and user could be the programmer, user could be the real user of the device itself. User could be programmer at different levels also, or the algorithm designer, or the problem generator. Someone who has a problem also is a user of the system. So the problems that we discussed actually affect all these parts. Clearly there are many new problems that we want to solve. I think problems of humanity is increasing for sure. There are many new issues that are coming at the bottom because we're pushing technology to the limits, right? And we're also exploring new technologies, and we'd like to enable new technologies. We'll cover some papers related to new technologies also in this, hopefully in this seminar, depending on what papers you select. And clearly users also change. And again, yeah. So as I mentioned, computing landscape is very different from 10 to 20 years ago. Basically, trends in software has changed significantly, and clearly humans are different also compared to when what they were 20 years ago, because they're not raised with technology as much. They were not raised with technology as much 20 years ago. And technologies and their issues are also changing, and the resulting requirements and constraints are also changing. So basically today we're in a situation where every component that we have in a computing platform and its interfaces, as well as how the entire system is designed, is being re-examined. And as a result we have these different types of components that some of which did not really exist, if you will, 20 years ago. And this picture doesn't do justice to it, because we have a lot more accelerators today, for example, than this picture depicts. Right? We have a lot of machine learning accelerators, for example, video processing accelerators. It could be somewhere here, but it could be also specialized. Okay, so we're going to touch upon a lot of these parts. Is this exciting? Okay, cool. So let me motivate you a little bit more based on some interesting things that have been happening in computer architecture. We didn't cover this in Digitech if you took Digitech. But since how many of you took Digitech last year in 2019? Okay, a good chunk. How many of you took computer architecture? Okay, so it's a mix. So in computer architecture you may have seen some of this, but not in Digitech for sure. So there's clearly very interesting things that have happened more recently. So from the performance and energy efficiency perspective, today we have a lot more specialized designs. But before we move into them, we have this thing, and this is phase change memory. Well, Intel doesn't call it phase change memory, but it's Intel's Optane memory. It's based on what they call 3D X-point technology. It's essentially main memory that's non-volatile. It could be used to replace DRAM, which is the main memory technology that's dominant. And this was introduced in 2019. And you could buy it. You need to pay a lot for it, much more than you would pay for DRAM, because the technology has not matured clearly. The manufacturing processes are still being perfected, whereas DRAM has 50 years of background, more than 50 years of background in front of it, right? But this is a disruptive technology that people started developing to replace DRAM. So clearly this is exciting because it has advantages. Your DRAM is volatile. When you power it off, you lose all the data. Here you don't lose all the data. Basically this is persistent, this is non-volatile. You can have non-volatile main memory this way. This is much faster than your SSD. It's similar in terms of speed to your DRAM. And today maybe the disparity between DRAM and this may be high, but over time as the technology matures, the speed of this will improve faster than DRAM. I don't think it's ever going to be as fast as DRAM, this particular technology itself, but there could be other technologies that could be as fast as DRAM. As they mature and as they're invested into, they could actually revolutionize the way we actually design computing platforms. So this actually enables much higher capacity main memory in a computing platform. So that clearly enables bigger applications, for example in a cell phone. But it also enables possibility of manipulating persistent data directly. Right now when you program, for example, you have it's ingrained in us to distinguish between volatile data and persistent data, right? If you need to persist the data and make sure that that data stays, I don't want to call it forever, but persistent, let's say, in hard disk, you really need to go through a file system interface. Right? Your normal array in your programming language, you manipulate it, but if you don't write it into a file, you lose it. Right? It's part of the main memory. So you have this dichotomy between main memory and volatile memory, main memory, and non-volatile storage. But if actually this becomes big enough and this replaces your volatile memory, now you can actually manipulate persistent data in the memory itself. Maybe you don't need to go through a file system, right? You can directly access this with loads and stores and update persistent data directly. Then the question is, of course, how do you design the system to make sure that that works well? So this is exciting, I think. Any questions? Okay, how many people were aware that this existed? Optimum. Okay, have you used it? Not yet. Okay. Yes.
The question is it like really forever stored, or is it like just a year or something and then it will decay?
That's a good question. So basically, its retention capability. Well, I don't know exact characteristics of this. You should read the specification that Intel provides. But with phase change memory, for example, the retention capability is more than 10 years, even at 85 degrees Celsius. So it's similar to what you have for SSDs. But of course, this particular product may have its own specification that Intel provides, and that I don't know. So it is non-volatile. Yes?
Would you say that it has some security implications as well? Because if you don't if you shut the system down,
absolutely, yes. Absolutely. Basically, this technology has advantages, also disadvantages. And one disadvantage is if you really want to get rid of the data that you have in your main memory, now you need to do something special to get rid of your data, because this is non-volatile, right? You need to erase it somehow, right, or get rid of it. Because if, why may you want to get rid of your data? Because if your device is stolen or somebody's sneaking into it, right, they may actually inspect your memory somehow, right? So that's one downside of this. And you may remember, I think we did talk about cold boot attacks in one class. I don't remember which class, but people actually even play those tricks with DRAM, because DRAM has some retention capability. If you steal, or if someone steals your cell phone, for example, they could freeze it. And they could enable the data to stay in DRAM for much longer, and then they could access whatever remains in your DRAM. So it could actually increase the retention capability. And you can imagine that this retention capability is much longer than DRAM over here, so this poses even more ability to launch such attacks. Yes?
Does the volting need to be supplied with power to access it, or is it like certain parts of it that have like their own system, so that you can, if you only need a small part of it, you can leave the rest part off?
Oh, you mean for this part, for this memory? Let me try to understand your question. You're saying if you don't need some parts of this memory off, can you turn them off?
Yeah.
Right.
Without affecting the rest. Accessibility of the rest.
Yeah. So I don't think you can do it in this particular case, but there's no fundamental reason why you cannot enable that by changing the architecture. So as an architect, I would say that you should be able to do that, but not all devices give you the option to be able to do that. Yes.
Is this already like kind of a solution to like the problem of the DRAM refreshing? As like, does it draw less power?
Exactly. So basically, this because it's non-volatile, and because essentially it doesn't leak like DRAM, so you don't need to refresh this memory. So it gets rid of the refresh problem, and that's essentially why it's a more scalable technology. Because if you remember from both courses, actually, refresh is a major scaling issue with DRAM. And this technology gets rid of that. Yes?
Are you sure that it has exactly the same performance as DRAM? Because as far as I know, it has higher latency. But
absolutely, yeah. It has. So it doesn't have exactly. It doesn't. It's actually worse performance than DRAM.
okay.
It may be 2x, 4x. Actually, I don't know this particular device, but the phase change memory technology we study have 2x, 4x, 6x worse latency than DRAM, and the write latencies are actually much worse. But you can overcome some of those latencies. So it cannot perfectly replace DRAM, actually. And we will have some papers that talk about hybrid memory systems in this course. So maybe the solution is really having multiple technologies at the same device. But there are some other technologies that have similar performance to DRAM, like some magnetic memories, which this is not a magnetic memory. This is based on phase change. Some magnetic memories have similar performance as DRAM. So they could be more promising, but then they have a lot of manufacturing issues right now, comparatively. So you cannot cram as many bits as this one in magnetic memories. Okay, this ignited a lot of discussion. That's good. But maybe we should read some papers related to this. Okay, so this is also something close to my heart, because we've been working on enabling some technology like this for more than a decade, if you will. And this was the first paper that we wrote on the topic. It was written in 2009. This may be in the paper list that you may select from. We started the work in 2007, and we basically wanted to. It was clear that DRAM scaling was hard, like scaling DRAM such that you get much higher capacity is hard, and we wanted to replace it with a more scalable technology. And phase change memory was a good alternative for us, and I still believe phase change memory is a good alternative. At least it was a more practical alternative. Some of the other technologies were interesting, but maybe less practical for us at that time. And you can see that the research, the early research, this is architectural research. There's also a lot of device level research that went into phase change memory, and this paper actually referenced a lot of the device level research. What we did was an architectural study. What happens if you take DRAM out of the system and replace it with phase change memory? And we found out that you actually lose some performance. And because of the fact that the latencies are larger in phase change memory, because of the fact that bandwidth is lower in phase change memory. And then the question for us was, how do you architect the system such that you minimize the performance loss? But you can have much higher capacity, of course, if you have a system like this. Anyway, this is close to my heart, and we'll probably read papers that are similar to this. But this also shows you that if you have an architectural idea, especially in a new technology, it takes time for that architectural idea to go into reality. Right? I mean, clearly we didn't make it reality. Intel made it reality, but it was important to do the architectural research over a decade. And there's a lot of architectural research that follows it. And there's a lot of device level research also. If you look back, starting from like, especially in the early 2000s or so, there's a lot of device level research that looks into phase change memory, and also how to read and write data fast and reliably into phase change memory. So you can, enabling this thing takes a lot of effort. And it's a completely different technology. Not only a lot of effort, but also a lot of money. Because the manufacturing processes for this are actually completely different from DRAM. And that's why they're not perfect at this point. And over time, I believe the latencies and some other aspects will improve. There are some reliability issues over here. There are some endurance issues, for example, that we didn't talk about that. But as you keep writing to a cell, you can do only so many number of writes to a cell. It's very similar to flash memory. And that poses some issues, of course, right? If you use this as your main memory, how are you going to manage this? You don't want your main memory to die, right? Because you keep writing to it. Okay, so there are a lot of interesting issues that are enabled by this. But it's important to do the research to actually enable this sort of technology. And if you're interested, you can take a look at these papers. Okay, as I said, this is 3D X-point. Intel never publicly disclosed what kind of internal storage that they use. But I believe it's really phase change memory. If you look at a lot of the publications that led to 3D X-point, a lot of people agree that it's phase change memory, even though Intel never publicly disclosed it. Okay, so that's an exciting thing. So there are other exciting things that are happening today. Has anyone seen this before? This is...
Wasn't it in the computer and Digitech? I think you mentioned that.
Oh, I mentioned that in Digitech? Really?
I think something similar.
Okay, maybe I did mention it. Okay, that's good. That's fine. Let's mention it again. It's interesting because this is something that's happened again in 2019 from a startup, not a big company this time, but this startup decided that they would build a huge chip. Remember the Moore's Law example that I showed you? In 2011, we had 2.6 billion transistors in the largest chip. That's 21 billion transistors in the largest GPU in 2019. And this chip that they built is 1.2 trillion transistors. And you can see the area, right? It's almost 50x difference in terms of area. This is 815 millimeters square. This is something like this. It's essentially a wafer. So why did they do this? Basically, they were designing for an important workload, in this case, training large machine learning models. And they wanted to accelerate it as fast as possible. And there's a lot of parallelism that you have in these large machine learning models, and you need a lot of data also. So you need to do a lot of matrix multiplications on a lot of data. So how do you actually get to store a lot of data and access a lot of data very quickly and also enable very high parallelism? Well, as opposed to having a single small chip, as opposed to cutting a large wafer into small chips, keep the wafer and make it a huge chip. Right? That's the idea. And this gives you a large amount of memory. You can now use it as memory plus computation logic. So this is a specialized accelerator for machine learning, especially training. Of course, you can do inference on this also, but especially training. And I believe one of the big benefits is the fact that they could fit a lot of data on this huge chip. And you can see that they claim to have 400,000 cores. I mean, they don't disclose a lot on this because they're a startup and they want to make money, clearly. But they have some information on these links, and you can find out more information about this. But this is something that's happening because of the demands of the workloads today. Right? The workloads are so demanding that you need this sort of different thinking. And this sort of different thinking is happening right now in 2019. You're really specializing for some algorithms, the chips that you design. Of course, this is not easy, right? Clearly, there's a reason why we get a semiconductor wafer and cut it into pieces. Because if you actually do manufacturing on a single wafer, you get a lot of faults. And if you cut it into small pieces, you basically reduce the probability of having all of your processors faulty, right? Now, if you use the entire wafer, or a good fraction of it, for your chip, you're going to likely get faults in a good chunk of this, right? Of course, now they need mechanisms to tolerate those faults. And these folks claim that they have some mechanisms. So of course, they don't disclose exactly what they are. But this is fascinating because now you actually can have a different design space, right? And also, powering up largest GPU takes a lot of power today, right? Imagine powering up this thing. This is 50x in terms of the computation capability. So you need some more advancements in cooling mechanisms, and these folks invested into cooling mechanisms also, and you can read about that. But again, there's not a lot of, this is not going to be a paper that we read in this seminar because they haven't written a paper about this. I assume if they're successful, they will at some point write a paper, but it's not going to be similar to the papers that we're going to read in this seminar probably, because usually when industry writes papers, they don't really go into a whole lot of scientific detail in terms of what they have included in their processors for various reasons. Well, one of the reasons is they don't want to disclose clearly, right? Because some competitor can actually replicate it and get ahead. Or there are also legal reasons, right? If they disclose too much, they may be sued by people who claim that they've done the same thing and they patented it, right? So there are interesting reasons why industry doesn't write as much in detail as the papers that you will see. Yes?
Do you have any idea what kind of transistor size they use for this?
So I'm not sure if they disclosed it, but yeah.
So what do you suspect? You can kind of, I guess you could kind of estimate it from the size.
Exactly, you can estimate it. I'm assuming that they use cutting edge technology.
Okay.
So, yeah, so I don't think it's a larger size than a GPU, for example. But that's my assumption. Yeah. Otherwise, they won't be competitive. Yes?
Like from a design point, isn't it kind of analogism to that what AIM did it with the chiplet design and like being able to scale out the architecture?
So that's true, yes. That's another approach, of course, right? Now you can have more, but I think the communication latencies in that may be higher. Because you still go from chip to chip over there, to chiplet to chiplet over there, whereas here you're on the same die, essentially. Yes, it takes a long time to communicate from here to here, probably. But as long as if you have a specialized chip, which and you know your workload really well, maybe you don't need to communicate from here to here, right? You map your workload such that you don't do that sort of communication. And this is a specialized chip. It's not general purpose, clearly. Yeah. Okay, but this is happening, and this is exciting, I think. And there are clearly a lot of trade-offs that you go into. And this is a design space that has not been explored as much in computer architecture. Okay, this is another example that was again introduced in 2019 from another startup called UPMEM in this case. And this is an example that we briefly talked about in some of the lectures. Actually, if you've taken computer architecture, we talked a lot about this. Basically, this is a DRAM chip with processing capability inside the DRAM chip. So you can see that these, they call it the PIM chip, processing in memory chip. And they have some sort of processing capability, which I'm not going to go into. You can read again their papers. But the interesting thing is that they actually were bold enough to go and change the DRAM design to add a processing element next to each bank. And now you can actually operate on the data that's very close to the bank itself. This enables high bandwidth, low latency operation on computation on data that resides very close to the computational units, right? You don't need to move the data out of the DRAM chip to the processing unit. So this enables higher energy efficiency also. Right? And you can exploit the parallelism that you have inside the banks. So you can see that things are changing in computer architecture. If you go back like 1990s, the landscape of computer architecture was not like this. At that time, there was a dominant paradigm, which is what you've seen in Digitech actually, at least you've seen early in Digitech. It's the dominant paradigm is you design general purpose processors that are heavily superscalar, pipelined, out of order, and they're the dominant paradigm. And people were improving on that incrementally. But clearly that paradigm did not fit well the workloads that were coming in the later times, right? And it was very difficult to also scale. There are multiple reasons. The workloads became much more intensive, that a general purpose couldn't handle them. A general purpose processor couldn't handle them so well. And GPUs were one of the first examples that actually went against this general purpose paradigm, because GPUs enabled graphics processing, but they didn't only enable graphics processing, they enabled a lot of other applications that fit well to the parallelism and the architecture of the GPU. And later other applications like machine learning, clearly people figured out that, oh, these general purpose processors are not a good fit for fast and efficient execution of machine learning applications. But there was also some other thing, improving the performance of that single processor using heavy pipelining, heavy superscalar execution, heavy out-of-order execution became too complex and too power hungry. And you started getting to the regime of incremental performance improvements. And people started thinking differently, and that led to, okay, why don't we, thinking that, okay, why don't we design multi-core architectures as opposed to trying to improve the performance of single core? And multi-core was one of the disruptions clearly in early 2000s, and that enabled more parallelism on a chip. But now people are, clearly multi-core was not the answer to many things, because there are other benefits to be gained. Because multi-core, again, is a general purpose approach, right? You have a multiprocessor on a chip, and it's general purpose. You don't get the benefits that you would get if you specialize your applications. If you specialize your hardware for the application that you're running. And clearly you don't get the benefits that you would get if you actually do processing in memory. So people are thinking very differently today, and this is a really great time to be studying these. So this is another example. Some people have seen this probably. This is Tesla's they call it self-driving computer. It's essentially another machine learning accelerator, I should say. Basically, these are accelerators that are specialized for the tasks that they execute on the self-driving car. Whatever detection mechanisms that they have, maybe pedestrian detection or whatever detection, basically. And if you want to know more about it, they have a presentation that's linked from here. But maybe they have some other things also that you can find online. But you can see that this also is pretty powerful, and it's specialized for machine learning. And you can also see that some other principles get applied over here because they care about the safety, or maybe this is good marketing for them. They basically have two chips that are executing exactly the same thing, and if they disagree, then they can find out that something went wrong, right? And maybe they can take some other action in the system so that they don't take the wrong action, right? So basically they use the principle of dual modular redundancy at the chip level. Two chips doing the same thing, and if they disagree, you know that something is wrong. It's a very old principle actually. It was employed in late 1970s by Tandem Computer. Has anyone heard of Tandem Computer? Later HP bought them. But these folks were designing very reliable computers for not only safety critical systems, but also transactional systems like banks. And banks used to buy their computers, and their key feature was dual modular redundancy. They basically coupled two processors. They would execute the same code on the same database. They would execute the same thing. And if they disagreed at the result of any instruction, they knew that something was wrong. There was some fault. And what they did at that point was, this Tandem Computer, they actually raised an LED, and that LED turned red. And now somebody who was monitoring the system could figure out which LED is red, and they could replace the computer. That LED was very important. That's the interface to signal that something is wrong in this entire data center of computers. Yes?
Wouldn't that redundancy feature imply that you would be able to use out of order to a certain extent? Because if they have different orderings,
yeah.
that would disagree?
So yes, absolutely. But then so you need to ensure that you compare things when they're retired. Yeah.
So precise exceptions.
Exactly. You need to have precise exceptions for sure here. Yes. Otherwise, yes, you may get a lot of faults that are not really faults. Okay, but this is also happening. Clearly people are specializing now for their use case, and a company that normally produces cars is producing its own chips. Now, these are produced by Tesla, and Tesla hires a lot of computer architects and people who design computers, which may not have been imaginable 20 years ago, right? Okay, so you've seen this actually, we've discussed this. This is one of the earlier machine learning accelerators that use systolic array principles. Actually, a lot of machine learning accelerators use systolic array principles to accelerate matrix multiplications that happen in machine learning inference as well as training. And this was Google's TPU, Tensor Processing Unit. And this may be one of the papers that you may actually pick as well, we may actually discuss. And they published this paper that looks at the performance of this tensor processing unit, and they make some claims saying that this is much faster than GPUs. So when we get to the paper, we can discuss it if we actually choose it. But this is another example of a specialized accelerator that's designed by a traditionally software company that has nothing to do with hardware initially, right? And this is generation 2 of TPU. Basically, it's designed for not just inference, but also training the models, basically figuring out what the model, machine learning model should be. And training is usually a much more intensive process than inference. That's why you need much more sophisticated computers and much higher bandwidth memory, as you can see over here. Now they have, I think, 3rd or 4th or 5th generation that are not necessarily disclosed to the public. But you already know the principles of systolic arrays from Digitech, so I'm not going to go over that. But we may actually cover some systolic array-based designs. And you can see that the system is actually, it's not just the accelerator, right? It's really a full system design in the end. How do you take the algorithm and actually make sure that the algorithm executes well on this specialized accelerator? In the end, it's a specialized matrix multiplication unit. But it's a big matrix multiplication unit. You can see that it can do 64,000 multiplications per cycle, right? That's a lot. They actually increase it later on, but this is the early first generation. But you can see that you need to ensure that the data that's coming needs to be buffered, needs to be set up. They need to be fed into the systolic array. At the same time, the weights are being fed into the systolic array such that the weights and the data match at the right time. If you remember the systolic arrays that we covered in Digitech, this is very important in systolic arrays. You need to match which inputs are match with the other outputs. You need to basically stage your data such that your data arrives at the right time in your unit. And that's essentially what they need to do also here. And for that, they need a lot of both hardware as well as software support in their system. Okay, and there are actually many, many other accelerators. People are designing many of these accelerators. This doesn't do justice to that, but traditionally software companies, this is actually something that I took off from some website. I don't know why this is cut off at the bottom, but you can find these slides online. Basically, these companies that have nothing to do with hardware traditionally, well, maybe one of them is not, well, traditionally, yes, they're designing hardware over here. Well, I guess it's not very nice because IBM clearly has something to do with hardware. But Google, Microsoft, Facebook, Amazon, they normally don't design hardware. Even Apple didn't design hardware until recently. Right? Hardware meaning microprocessors. Right? Okay, so there are other interesting things happening in, any questions so far? So this is the performance and energy efficiency. I could go on and on in terms of performance and energy efficiency, but you could examine some of the designs from these companies also. We've also discussed some other things like reliability and security. I'll go through this relatively quickly because we've covered this. Clearly many of you, how many of you know about RowHammer? Okay, everybody. So I'm not going to cover this in detail. I'm going to skip this relatively quickly. But this is also relatively recent, right? And as you know, this is something that's not supposed to happen, but it's really the first example of how a simple hardware failure mechanism creates a widespread system security vulnerability. And clearly it's exciting to people who are more software people because now they can actually enable this sort of attacks that exploit physics, right? Okay, basically you hammer a row, you keep activating and pre-charging a row, and that leads to bit flips in adjacent rows. That's the idea of RowHammer. So I'm going to go through this quickly. That may be one of the papers that we may read also. And also some of the attack papers that build on RowHammer, maybe some of the papers that we read. And clearly many chips are vulnerable to this, and this was the original paper that we wrote. And later there was a lot of exploitation of it, and we will see some of those papers potentially. And we actually recently wrote this paper that looks retrospectively at what has happened over the course of the 5 years since we've written the previous paper. And a lot has happened actually. in terms of the RowHammer space. There were a lot of attacks, there were a lot of solutions, and there were a lot of analysis also, and you can read this paper if you're interested. Maybe that'll be one of the papers, we'll see. How many of you know this one? These meltdown inspector. Okay, I'm going to go through these relatively quickly also, but these are also relatively recent. I mean, if you think about the grand scheme of things, RowHammer is really 2012, 2014. This is 2017, 2018, right? And RowHammer is perhaps how should I call it? Most stark example of technology scaling difficulties, right? Because this sort of bit flip should not really be exposed to software, but it is being exposed. But this is something completely different. It's not about technology scaling. It's about how we really design execution engines, general purpose execution engines. And basically, people did not have the security mindset when they were designing execution engines for decades and decades. And they couldn't anticipate something like this. And in my opinion, it's very hard to anticipate something like this if your goal is to improve performance. But basically with meltdown inspector, someone can steal secret data from the system, even though everything is correct. Your hardware behaves according to the specification, and there are no software vulnerabilities and bugs, because speculative execution that we rely on leaves trace of secret data in the processor's cache. Basically, it brings data it's not supposed to bring if there was no speculative execution. And a malicious program can inspect the contents of the cache to infer the secret data. A malicious program can still not directly read the secret data because it's protected by virtual memory mechanisms, but they can infer that secret data through side channel mechanisms, right? And this is fascinating, clearly. And a malicious program can actually increase the probability of the attack by forcing another program to speculatively execute code that leaves traces of secret data in your processor. So clearly this is very much ingrained into the internal workings of a microprocessor, right? And people were able to figure these out because they started having this mindset that hardware is vulnerable. And actually it's very interesting to see the progression of this. Security community did not care much about hardware if you look back 20 years ago. There was a very niche part of security community that was looking at hardware. Now a lot of people's hardware security is a really big area because a lot of people think that these are the attacks that are the hardest to defend against. If you find a software bug, you can patch it. A lot of the security issues come from software bugs. Those are actually, a lot of the attacks happen that way. But these are not only hardest attacks to launch, but also hardest attacks to defend against. And you may not even know who's launching these attacks sometimes, right? Who knows who's launching these attacks, right? Okay, if you're interested, you can actually read this blog post by Project Zero on Google Project Zero on Meltdown Inspector. Okay, there are other things happening in computer architecture, basically more demanding workloads. They're actually driving the demand significantly. If you haven't taken Digitech, we didn't cover this one, but there are genome sequencing technologies. If you've taken computer architecture, we had a lecture related to this. But this device is very interesting because you can buy it for relatively cheap, $1,000, $2,000, and you can sequence a genome with it if you have the setup for it. So it basically reduces the cost of sequencing a genome, which means that you can actually sequence many, many genomes, if you wish, and very cheaply. That means that you're generating a lot of data. But of course, if you can sequence genomes, now you can actually ask a lot of questions to understand what's happening, or many questions basically that you would like to ask by sequencing genomes, right? And this is actually very interesting. We don't need to go into the technology, but we may read actually papers related to this. So for example, you can ask, if you imagine that you had a device like this. So this device doesn't have processing capability. This device just generates, takes a genome and gives you what the sequence is like. It's not perfect, it gives you pieces of the genome. Then you need to piece together what those pieces look like to ask questions to it. So you can ask questions like, am I vulnerable to this disease? Clearly. You can ask questions about your ancestry. You can ask questions about whether this treatment would work for you. You can ask questions about which viruses are similar to which other viruses. So you can actually compare an unknown virus to many, many millions of viruses that you may know of. And this is an important topic these days, as you can imagine, right? And these devices are actually being used for that purpose. But these devices actually generate a lot of data, and they actually cause a lot of performance and energy bottlenecks. So designing specialized architectures to take advantage of these devices is becoming very important. And actually, we will probably discuss this with some papers. If you're interested, you select some of those papers. But this is something that I put up recently over here. You can see that this company that has produced that Minion device has been sending a lot of these nanopore sequencing devices to China so that they can do a lot of basic on-site detection, or relatively real-time detection they call it. I don't know how they exactly use it, and they don't provide a lot of detail, but clearly there are use cases of sequencing these viruses and understanding what other viruses they resemble. Okay, is it interesting? Okay, they also use it for RNA sequencing. They don't do it just to DNA, but they do RNA as well. Okay, but I mean, there are other sequencing devices also. The interesting thing about this nanopore device is that they're relatively small and they could be used for embedded purposes. You can carry them, right? And you can ship them like this. You can see that this is 700 kilograms, but there's a lot of them. But there are other devices that look like this. This is the previous generation technology. This was also a breakthrough in genome sequencing, but these devices are much bigger and much more expensive. It's more $3 million per device. They're high throughput. They're even higher throughput than the nanopore, but they cannot be used in an embedded purpose. You cannot, actually, nanopore was used in Africa by many researchers to sequence Ebola viruses or different types of viruses, for example. You cannot carry this machine around and sequence things, right? It's bigger than you, actually, on some of these machines. But there are a lot of technologies that generate a lot of data, and that data needs to be analyzed and analyzed more so that you can get to scientific discovery or medical benefits. And that analysis is actually very complicated. I'm not going to go through this right now, but in the end, you're really bottlenecked by the performance and energy that that these devices consume or provide, or your computing devices consume or provide. Okay, so this is a workload that I think is going to be even more important going into the future, genome analysis workloads. And I think there are other examples in medicine and health. You can imagine anything related to human life or nature is a data source that comes into these devices that could be analyzing what's going on in nature. And maybe you could actually predict an outbreak like coronavirus much earlier than it happens, right? Of course, we don't know the cause of this yet, so we will see. But maybe there are ways of actually predicting these things. Okay, there are other more traditional workloads that are becoming more intensive, clearly, and you see there are a lot of papers that are being written about these workloads showing that the data that's processed overwhelms modern machines. Because data is really a performance energy bottleneck. And even in the, I don't want to call this the lower end, I always keep thinking about calling this the lower end, but it's really the mobile end. And some of the fastest and highest performance processors are inside here, actually. And even on that end, there are a lot of workloads that are bottlenecked by performance, bottleneck in terms of performance and energy because of data. And this may be one of the papers that we read, I'm not sure yet. But recently we've done the study with Google, and we showed that more than 60% of the entire system energy on these workloads are essentially spent on data movement between the memory hierarchy and the processor. That's why it's interesting to examine new processing paradigms like processing in memory. Okay, what else? I think I will stop here, but I will talk about some of the novel concepts. So basically, there are many novel concepts investigated today to tackle with these challenges that we have. There are new computing paradigms. We're going to read about a lot of these, I think. Rethinking the full stack, I think of it this way, basically processing in memory, processing near data, neuromorphic computing, or fundamentally secure and dependable computers, which I don't think anybody has fully tackled yet. How do you design them? How do you design the computing paradigms for them? Yes.
What is neuromorphic computing?
Oh, essentially, you can think of it as an imitation of a neuron. So you have a spiking neuron, and the circuit is designed to imitate that spiking. And you have an interconnect that connects the neurons, and you're basically imitating how our understanding of how the brain works. And you're doing computation with that understanding. It's currently it's limited in terms of what it can do, but if you can generalize it somehow, it could be actually a more general purpose computing paradigm. People have shown that you can do this for recognizing objects, for example, or moving arms, things like that. Basically, more physical functions that are similar to what you do as a human being, these devices can do at very low power. So the benefit, a lot of the benefits of the existing neuromorphic computing devices is that they've shown that they can do some of these tasks very energy efficiently. Okay, maybe that's a paper that we should read also. Okay, so clearly there are new accelerators. I call this algorithm hardware co-designs for very different applications, and you can also pick your favorite application over there. People are designing. Whenever an application is demanding, there will be an accelerator for it. And graphics, in my opinion, is one of the first ones over here. Clearly we have graphics accelerators are everywhere pretty much today. There's a graphics accelerator over here, and you can use those graphics accelerators for other things also, right? It's not clear if some of these other accelerators can be used for other things because they may be very specialized, right? And then new memories and storage systems. We're going to read a lot about that also. Okay, so I think I've already said this. Basically, today we're re-examining every component and its interfaces. Yes?
What is intelligent memory?
Yeah, so I think we're going to get back to that. It's a very general term, clearly, right? It could be processing in memory is one sort of intelligence, meaning you can do computation in memory. But it could also be that, if you remember, we talked about memory controllers in Digitech. And if I look at this machine, I had this machine for 5 years. And its memory controller is very stupid. What does that mean? It hasn't learned anything in those 5 years. Okay, let alone 5 years. It hasn't learned anything based on what has happened in the last microsecond. What does that mean? It's doing exactly the same thing the hardware designer told it to do, right? Even though it has seen a lot of data, that data just comes from here and goes from here, right? Meaning it hasn't really adapted its scheduling policy, for example. Whereas maybe an intelligent memory controller observes what's happening in the workload, in the access patterns, and it adapts its scheduling policy so that you could maximize performance, minimize energy, or maximize reliability somehow, right? So if you understand what's going on as a hardware agent internally, you could change what you're doing. And that's one example of intelligence, right? Intelligence is clearly much broader. But we will, for example, have some papers that talk about using machine learning algorithms in the hardware design itself. How do you use machine learning to improve decisions that you make in the memory controller, for example? Okay? Okay, so I'm going to skip this one because we've already talked about this. So I think I mentioned this in some classes, but basically today is a good time to be studying these topics because you can actually have a lot of impact by thinking in the right way. You can invent new paradigms for computation, communication, and storage. And I keep recommending this book. Has anyone read this book? It's a structure. Oh, you have read it. That's great. The Structure of Scientific Revolution. It's the philosophy of science book. Basically, it analyzes how scientific revolutions happen, how big change happens in science. And Thomas Kuhn, who is a philosophy of science researcher, he wrote this book, and he basically said that science operates in cycles. And at some point, you have normal science, meaning there's some dominant theory that is used to explain things, and that's the business as usual. He gives examples from astronomy also. For example, the dominant theory at some point was the sun revolves around the earth, right? And that was the dominant theory. And people explained things using that dominant theory. And there were exceptions. And people thought those exceptions, they're anomalies. They don't really bother me. But over time, exceptions grew. There's more evidence that comes up that contradicts that dominant theory. And at some point, a revolution happens. Meaning that at some point, there's so much evidence that you need to change the theory. Oh, actually, it's the earth that's revolving around the sun because there's so much evidence points that is pointing to it. And I think this, so how do you get to that point? Basically, if there are enough exceptions, there's no clear consensus in the field, and there's some disruptive examination that happens. All of the underlying assumptions of the dominant theory is re-examined, and then you reach a new theory at some point. Of course, this is science, and maybe there is a single theory that explains a particular phenomenon. In engineering or computer architecture, I think my analogy is that there's a design that is dominant at some point in time. And I think in the 1990s, it was this design that we discussed, superscalar out-of-order pipeline processors, general-purpose computers, designed that way. And there were exceptions to it, right? Graphics was one exception. Okay, graphics doesn't fit well, so maybe we handle it using some specialized SIMD instructions that we add to this general purpose paradigm, right? So you actually basically start patching the paradigm. And there are anomalies in the end. And they're not general enough. But over time, these exceptions increase. There are more and more workloads that do not fit this particular design really well. And as a result, now we're in the point that we're not in normal science. We're not doing business as usual anymore. There's no dominant way of designing things. There are many, many possibilities of designing things, and people are designing a lot of different accelerators. So I believe we're actually, in this period right now, we're really examining the underlying assumptions with which we design computing platforms today. And hopefully, maybe, I don't know if this is a perfect analogy, of course. This is clearly a theory also that was developed by Thomas Kuhn, and he cannot really, this is not an experimental theory, right? Clearly he can show case studies that this makes sense, but he cannot prove that this makes sense, because philosophy of science is in the end philosophy. It's not a scientific discipline. So I don't know if there will be a clear consensus in the field of computer architecture, but maybe the consensus will be that we need heterogeneity at the massive scale, because workloads are very different, and if you really want to get the best of different workloads, you need to specialize for different things. And specialization comes in many, many ways, clearly. Okay, so if you're interested, I'd recommend reading this book. Okay, basically my takeaway is that it's an exciting time to be understanding and designing computer architecture today. There are many challenging and exciting problems which we will cover in this course. And some of it's no one has tackled before, right? Like RowHammer, Meltdown, and Spectre, these are new, completely new. And even ML accelerators, machine learning accelerators, they're completely new, right? These happened because people were able to execute. Actually, the reason the machine learning accelerator field grew so much is because of GPUs, I will say. These machine learning accelerators, people figured out how to train large models and also do inference on large models using the power that's provided by the GPUs. And after that point, in 2012 or so, people said, okay, we can actually train even bigger machine learning models. And then later people realized that even GPUs are not a good fit. Why don't we design specialized accelerators for it? Right. So that's relatively new, as you can see. And clearly there are reasons for it. We're hungry for more data, more analysis of that data, new applications, even greater realism, and that's not going to change. And we can easily collect more data than we can analyze and understand, because technologies enable us to do so. And also there's another aspect. This is the more higher level, application level aspect, but there's also the lower level aspect. We have significant difficulties in keeping up with that hunger at the technology layers. Technology is not scaling as well, so we're in search of new technologies. Quantum computing is one of them, for example, but I believe that it's actually much farther out than we may think it is, in my opinion. At least for computing devices. From a physical perspective, it may be better understood, but how to take advantage of that as a computing substrate seems to be not so easy because the technology is not there yet. And we're going to cover some of these difficulties like energy, reliability, complexity, security, and scalability in this course. Okay, well, this is a seminar, I should say. So I'm going to cover some of these. Basically, applications will continue, no question about that. And we have increasingly diverging complex trade-offs. This picture you may have seen before. But basically, computation is not a big problem anymore. In the past, it used to be a big problem in terms of energy. But today, memory access is a much bigger problem compared to computation. So as a result, a lot of the focus, even in those accelerators that we discussed, are actually on how to optimize the memory access. So this picture is from Bill Daly's keynote. Bill Daly is a chief scientist at NVIDIA. And basically, in this picture, it shows that memory access consumes 800x the energy of a relatively sophisticated double precision floating point operation, right? Now the question, of course, a good question to ask is, if you don't have good locality, if your caches are not working well, does it make sense to bring two pieces of data by doing two DRAM accesses to do this computation on chip, and then do another DRAM access to write back the result? So you're basically consuming 3 times 800x energy to do a simple arithmetic operation. Not simple, a sophisticated arithmetic operation that's relatively energy efficient. So it's good to keep that in mind. And then the next question is, okay, clearly this doesn't make sense from an energy perspective if you are completely random access. Then the next question would be, when does it make sense? Meaning, how much reuse should you have on a data element that you bring on chip, that this trade-off of bringing data on chip makes sense, right? Because clearly there should be a trade-off point. If you're reusing the data a lot, like thousands of times, probably it's okay to bring that data and then reuse it on chip, because on chip access is much faster, as you can see also over here somewhere, like this 256-bit access and 8 kilobyte SRAM is 50 picojoules only, which is similar to this 20 picojoules. So bringing on chip makes sense actually at some point, but you need to have very good amounts of locality to be able to do that, or reuse. So it's good to think about these things. And actually this is, I was in the DAC Design Automation Conference in June in 2019, and there was a special session on machine learning accelerators. And it's always good to try to understand what this trade-off looks like. And one person who was designing machine learning accelerators was giving numbers in terms of the disparity between the memory access and a floating point multiply and accumulate. And they said that in their system that they designed, a DRAM access costs 160 times the energy of a floating point multiply and accumulate, which their accelerator is designed to do. So in the end, they end up designing for minimizing the memory access as much as possible. Okay, so keep this in mind. Actually, before we go, if you go back like 5 or 70 years ago, and if you try to get these numbers, which is not an easy task, it turns out an arithmetic operation was much more costly than a memory access at that time, about 2 orders of magnitude. So within the course of 70 years or so, things have changed about 5 orders of magnitude to the other side. Why? This is again technology scaling. Scaling, when you scale technology, you're reducing the size of logic gates, certainly transistors. But your interconnect is not scaling as well. And most of your memory access is really interconnect in the end. So you're reducing the size of your logic gates. As a result, this is becoming more efficient, an arithmetic operation. But your memory access, which is dominated by interconnect, is not scaling well. As a result, we're at this trade-off. So if you can somehow get rid of the interconnect bottleneck, which is also very interesting, I think, then you can potentially get rid of this huge disparity. Or if you can somehow find a way to reduce the impact of the interconnect on the system. Okay, so past systems were relatively simple. Today's systems are much more sophisticated and complex. Okay, now let's talk about this course. Any questions so far? Okay, I will not take a break since we started late, but I'll introduce the course and then we will stop. So basically, hopefully, the goal of this course is to cover fundamental and cutting-edge research papers in computer architecture. And we have multiple components aimed at improving your technical skills, clearly, that's important. But even more importantly, critical thinking and analysis. The reason we will analyze papers, and it'll be very important to analyze them with a critical thinking and analysis perspective, questioning everything, basically. And of course, the goal is to improve your technical presentation skills of concepts and papers, ideas and papers, communicate them well in both spoken and written forms. We will have a written component also at the end. And hopefully this will increase your familiarity with key research directions. I've already given you some examples, but we will see more as we cover more papers. And the key goal is really this, I would say. Hopefully you will learn or become better at how to rigorously analyze, present, and discuss papers and ideas in computer architecture. But I hope that you can delete this. I hope this will be useful for for you to discuss and analyze and present papers and ideas in any domain. Because some of these are very fundamental. They're not necessarily related to computer architecture. Okay, so there's clearly some steps to achieve the key goal. So one of you will be the presenter, and the rest of you will be the participants for every session. The steps for the presenter are outlined here. There's an algorithm, kind of. So you read clearly the paper, you absorb and read more other related works that, than the paper that you choose. Usually reading the papers that are referenced by this paper could be useful, or reading the papers forward, meaning papers that build on this paper that you're presenting, is also useful, and your mentors can help with this. Critically analyze the paper, think and synthesize potentially. Synthesize meaning that maybe put this in the context of other works. And prepare a clear and rigorous talk, present, answer questions during the talk, and in the end analyze and synthesize in the meeting after and at the end of the course. So we will have a report at the end where you will have the opportunity to synthesize. So it'll be fun, I think. For the participants, it's important to participate since this is a discussion, and you guys have been doing really well so far, participating, which is good. So discussion is important, asking questions is important. Reading the paper is important also. Please try to read the paper beforehand, or at least skim it. I know it's going to be a lot of papers, so I am not requiring everyone to read every paper. Then that'll be a bigger course than what it is. But doing this will make this much more informative and interesting for everybody. Okay, is this clear? Okay. So these are some of the topics that we will cover. You will see the paper list when we get to it, but it's basically similar to what I've discussed so far. If you have any suggestions, feel free to email us also. I haven't done this before, I haven't taken suggestions, but feel free to email us if you have any suggestions for papers. That doesn't mean that I will take that suggestion, but I will take it into consideration. Okay, so some of the goals, like I think the biggest goal is really to enable you to think critically, think broadly, because we'll cover a broad range of topics, and we may actually have broad questions during the discussion. And hopefully you will learn how to understand, analyze, and present papers and ideas. And get familiar with key first steps in research, because reading papers is actually a very good key first step in getting into research. You read a research paper, you analyze it, you think critically about it, and you may have an idea to improve it. Or you may have no idea, you read the next paper. Or you may have no idea still after that, you read the next paper. And at some point, things click and you may have an idea at that point. And you get familiar with key research directions clearly. So this is the virtuous cycle of scientific progress as I think of it. You basically understand the phenomenon, understand the problem, and reading and critiquing papers is a good way of getting into that phenomenon or problem. And then you question and brainstorm, and then you develop new out-of-the-box ideas based on that questioning and brainstorming, potentially collaboratively, and usually collaboration is a very good thing over here. Actually, across the entire thing, collaboration is good. Collaborate. Well, there's a lot of hard work that goes into research, no question about that. I mean, you may have an idea actually in research, and that to prove that idea, you spend hours and hours of work. So I think of this as, for this 1% pearl, you put 99% sweat in the end. Or maybe for the 0.01% pearl, you put 99.99% sweat on the infrastructure to show that your idea actually makes sense. Okay, and then you do research, great research, and publish, and educate others more and more, and then you go back to this, it's clear, right? Or somebody else reads and critiques your papers and goes through this virtuous cycle. Okay, so let me give you some course info on logistics. I mean, I think all of you know me, so I'm going to skip this one. We have a bunch of teaching assistants, so you can actually look up on the course. I'm not sure if this list is up to date, by the way, but get to know them and their research also, and they will be your mentors. So these folks, the up-to-date list will be online. This slide, I don't think I got a chance to update. But they will be your mentors, and you will have to meet them at least twice before your presentation. So we will talk about that in a little bit. So these are the requirements and expectations. So I will require attendance for all meetings. There's a sign-in sheet. Do we have the sign-in sheet today? Okay, we don't have the sign-in sheet. So now that's going to come in. Unless there's a better way of signing in. But we're still going to use old technology, which is paper and pen. That could be the most non-volatile technology, potentially. I don't know. Actually, people are looking into glass as very non-volatile technology, etching things in glass. There's work that's going on in Microsoft Research Cambridge that looks at storing long-term data on glass. That could be interesting, right? Okay, anyway. Each student presents one paper, so you prepare for the presentation with engagement from the mentors. There are two mentors. Full presentation, questions, and discussion. That's the entire thing. We'll go over that also. So non-presenters hopefully participate during the meeting. That's good for everyone's experience here. So ask questions. Don't think that your question is dumb. Please ask. Contribute thoughts or ideas. And it's of course better if you skim or read the paper beforehand. Or even if you read the paper while it's being presented, that helps, in my experience. So I've attended a lot of meetings where papers are discussed before publication. So you actually attend these meetings in scientific committees, and you're trying to decide whether a paper should be published. And clearly there are multiple folks in this meeting, but you don't read all of the papers before they're discussed, because like 400 papers get submitted to a conference, and clearly I don't have time to read all 400 of them. I read a subset of them, but I want to participate in the discussion. So what I do during that time is, while the person who has read the paper and who's leading the discussion is presenting the paper, I'm also skimming through the paper and trying to find questions or poke holes into the paper, so that I can be comfortable in making decision of recommending this paper for publication, right? It's a very similar role, except here you have less time constraints. So in those meetings, usually the papers are presented within 5 minutes. The presenter presents within 5 minutes and the committee needs to make a decision. Of course, there are some cases where the discussion becomes longer, like 10 minutes, 15 minutes, but usually you don't have the luxury of having 30, 40, 50 minutes per paper. Because imagine it's 400 papers. If you have 30, 40, 50 minutes, it's going to be days and days of meetings. Okay. So reading and skimming, even during the presentation, is helpful. Of course, this helps if you're a good multitasker. Right? Okay, everyone comments on papers in the online review system after presentation, so it'd be good to have a discussion, and we will prepare something. This is still in the works, so that we can enable you to discuss online. And at the end of the semester, we'll write a synthesis report. There's a sample synthesis report online, actually, that you can look at. Okay, this is the course website. All materials will be posted here. And plus, there will be some other useful information for the course. So please check frequently. So there is a homework 0. This is going to be information about yourself. And all future grading is predicated on homework 0. So if you don't submit, you don't get a grade in the course. Well, even before that, you cannot be scheduled for a presentation. But this is very easy. It's just basically questions about why you're taking this course, what is your interest. It's okay to say I'm taking this course because it's a requirement. How many of you are taking the course because it's just a requirement? Don't be shy. Not because you're interested. How many of you are taking the course because it's an interesting topic? Okay, that's good. How many of you are undecided? That's fine. Okay, so paper review preferences. I'm not sure if some of these dates are actually correct at this point. We may actually revise these dates, but currently we're targeting February 26th so that you can submit your paper review preferences. And these are, it should be presentation preferences actually. These are the papers that you will rank in terms of, okay, I'm interested in presenting these papers in this order. And in the end we will decide who presents which paper based on the preferences that you provide. We will try to assign you the highest ranking that you provide, but it may not always be possible since there may be contention clearly between multiple people for the same paper, right? Okay, any questions? So please submit these on time so that we can schedule presentations over the course of the semester. And we have 22 folks according to registration, and we have 11 slots, and we have very little slack in terms of the schedule. Okay, so now I'll spend the remaining time on how to deliver a good talk. Any questions on the logistics? Okay, these will be relatively simple. So this is my anatomy of a good paper review or talk. And I think review, even if it's a written review, it's good to follow this anatomy or principles, right? In this case, you're going to give a talk, but if you're doing a written review, it's very similar. So first, present the title, authors, and venue. That's really important. I've seen many presentations where this is omitted, so I have no idea who has written this paper when it's presented. It's important to keep this. And then summarize the paper. And I'm going to show you an example of this in the next lecture. So you will see an example. But summary should cover what is the problem that the paper is trying to solve, what are the key ideas of the paper, what are the key insights that are provided, what are the key mechanisms that are provided by the paper, what is the implementation, what are the key results, what are the key conclusions. And you may actually need to go into some more detail to explain these things clearly, right? But having this key things are really important. And then you go into analysis. So this is some summary. It may take some time, as we will see in the next slide. Maybe 20 minutes, maybe 15 minutes, depending on the paper. Some papers actually take a longer time to explain. Like the Meltdown and Spectre papers are actually relatively sophisticated, so you may actually need to explain them much longer. But then you go into the analysis mode, which is you talk about the strengths of the paper and most important ones. Basically, does the paper solve the problem well? Is it well written? And you will see examples of it. It's very important to order the strengths in terms of order of importance. So the most important strength should come first. Right? For example, this is a really creative, brilliant idea that had significant impact on future research. That's probably a very big strength, right? As opposed to, this is a very well-written paper. By the way, you will see not well-written papers also. So well-written paper is also strength compared to not well-written paper. But clearly, writing issues are not as important as the idea. Of course, sometimes, well, in terms of strengths, hopefully writing is not the only strength of the paper, right? Let me put it that way. Usually, the brilliance of the idea comes first, and then the novelty of the idea also comes at the high levels, and then the mechanisms, the creativity of the mechanisms and the solidness of the mechanisms are also high up there. And then the goodness of the implementation comes, and then the evaluation also comes. Evaluation is also important strength, but again, that cannot be the only strength. Of course, this depends on the paper, right? Some papers are solely evaluation papers, not an idea paper. In that case, evaluation may be the most important strength, because that's an evaluation that no one has done in the field so far, and that could be an important evaluation, right? But usually a novel evaluation is much more important than a not novel evaluation. So keep this order in mind. And then writing issues and other issues may come. Weaknesses are actually, this is where you need to think critically, because strengths are more or less relatively easy comparatively to determine compared to weaknesses, because when people write papers, they try to argue for what they're proposing, right? And they usually argue in a nice way, assuming the paper is well written, so they actually pose you the strengths. Of course, there are cases where people write some paper and they haven't anticipated some use case, so there may be some other strength that appears for that paper that is not covered by the authors, right? And that happens a lot also. But weaknesses, usually you need to distill it yourself, because usually papers don't tell you what the weaknesses of the mechanisms are, partly because they may not know it at that point, and partly because that's not necessarily what they're showing, right? So there's usually a bias towards strengths in science in general, which is not necessarily good, I'm saying, but that happens. Because the goal is really to design better mechanisms going into the future, and also partly because they may be working on the weaknesses that they're going to fix later on, right? That's also important, right? Okay, so and this is where you should really think critically. And every paper and idea has a weakness, no question about that. This doesn't mean that the paper is necessarily bad or unimportant. It means there's room for improvement, and that's true for every single paper. And future research can accomplish that improvement, basically. And again, weaknesses should be ordered in terms of most important to least important. And the order that I proposed earlier for strengths is similar. So so for example, you can question the problem. If this problem is completely unimportant and the paper is solving a already solved problem, that's a pretty major weakness, right? I don't care how well the paper is written at that point. So that's a much secondary concern. Or I don't care how well the paper is evaluated, because it's on a problem that's not relevant. Of course, while doing this, you should be also careful, because you may think the problem is not relevant or important, but there may be cases that problem may be very, very important and relevant. So it's good. This is where you need to also think broadly, because there may be some niche domain where that problem is extremely important, right? Like maybe the problem, maybe you don't need that much safety critical execution on this sort of computing device, but if you're designing a computer to operate in space, that's a very different design constraint, right? Okay, so keep this in mind. So this is where a lot of discussion will come, and this also what enables future research really well also, because you realize a weakness, or you're inspired by something that this paper doesn't solve, and that leads to some new research. And then, can you do better? This is also, of course, always good to think about. Can you do better? Do you have any new ideas on top of this? And I've seen good ideas presented in these seminars, so believe in yourself that you can generate good ideas. And then takeaways, what you learned, enjoyed, disliked, and why. And then, of course, the next step is really starting the discussion. Of course, if the discussion is happening while you're presenting these things, that's always good. But sometimes the function of the lead, the person who's presenting the paper, is to actually ignite the discussion or make the discussion flourish even more. And here you can actually have some questions that you can ask about the paper. And the more relevant those questions, the less general purpose those questions are, the better. Meaning you can always ask the question, is the paper evaluated well, right? I can ask that question for every paper. It's a discussion starter, sure, but try to refrain from those general purpose questions. Try to make it more specific to the paper. And basically the review should be short and concise. Again, if it's a talk, maybe 20 minutes or so. Well, actually I have a better suggestion over here, which is this. So I would suggest summarizing the paper in 20-25 minutes or so, and then spend about 20 minutes for critique and discussion. And that takes us to about 45 minutes per paper in the end. And I assume we'll take 45 to 50 minutes per paper. Does that sound good? Yeah. We'll see an example of this next week, since we don't have enough time this week. Okay, there's some more advice. I would suggest being very critical, because that really what enables you to really be a better scientist and also a better idea developer. Always think of better ways of solving the problem or related problems. Question the problem as well. Read background papers. And again, this is how things progress in science and engineering, or anywhere really, actually. Even if you're doing not science, basically if you're in business, somebody presents an idea to you, this is actually how you improve the idea, right? It doesn't matter what field you're in, and this is how you can change things, by critical analysis. We have a few sample texts provided online, but they're not going to be useful for the purpose of this course at least. Okay, this is something I will recommend also. Try to avoid rat hole discussions. And there are some rat hole discussions that may happen, and they usually revolve around these things. Actually, there's a better picture of this, I think, that one of your mentors found last year, Minesh. I think I should use that picture perhaps, because it also has the relative sizes of these things. But I'm going to show you another picture that shows the relative size. Basically, you can always question the workload, especially in computer architecture. You can always question, can this idea work on this particular workload? And you may not get the answer from a paper, because it's impossible for a given work to evaluate all possible workloads in the world. Right? So this is a rat hole discussion, in the sense that, yes, mention it, but don't harp on it. This may not work for this workload. Yes, that's true. Okay, metrics is another one. Maybe they didn't evaluate all possible metrics, and that's usually true. You cannot evaluate all possible metrics that you can potentially evaluate the design with. You can question the metric that they evaluate with. And if there's a fatal flaw, of course, in the metric that they evaluate, that's a big problem, of course. But they didn't evaluate metrics X, Y, Z. Yes, that's a weakness, but you cannot evaluate all possible metrics clearly. Configuration details, that's actually also important. This is smaller rat hole, so this is a bigger rat hole. You will see the picture later on. But you can always question the setup, experimental setup, saying that, oh, this is not realistic, that's possible. Or you can say that this is too aggressive, or you can say that, oh, they didn't evaluate all possible combinations, now it's becoming insurmountable, right? Because in computer architecture we have so many knobs in a system that it's very difficult to evaluate all possible cases under which an idea could potentially be employed. In fact, in many cases, even when you're writing the paper, you may not even know what's the best configuration under which your idea is useful. And that's the interesting thing, right? You can do your best in evaluation, and you write the paper, and you show some benefit, but maybe the best case of your idea is something completely different, right? In some other setting. That's why it's really important to expose good ideas without being too much constrained by these things. These things are workload, metrics, and evaluation setup, because someone else can figure out a way to actually take advantage of that idea in some completely different way that you thought of. Like systolic arrays is one example. I'll pick that example because it was initially developed for image processing applications, and later people figured out that they were a great fit for machine learning applications right now. So everybody's using systolic arrays for machine learning today. Maybe that's not the greatest example, because image processing and machine learning, they're actually similar in terms of, at least neural networks are similar in terms of how they behave. You have a lot of matrix operations in both. But anyway. But clearly, when systolic arrays were first developed, they didn't evaluate the machine learning workloads, and nobody asked them to evaluate the machine learning workloads. Okay, so I would recommend this book also. Actually, this picture is borrowed from this book. Has anyone seen this book? You have seen it? You've studied it? Or? Okay, I see. So if you, some courses use this book if they're on performance analysis especially. So this book is very useful actually in many aspects, and I would recommend reading it if you have fun reading books. But I really like this book for multiple reasons, because it's actually a very interesting book in terms of all of these things: experimental design, measurement, simulation, modeling, theory, scheduling theory. But it also has a lot of interesting insights, tidbits that are inside the book. Yes?
So how do you, because it was written so long ago, how does it compare to like
Yeah, so I think a lot of these things that are discussed in the book are so fundamental that they're not dependent on the technology itself. Some terminology may be relatively old, but even then I think I would recommend this book. So the fundamental aspects of it is really good. There are some new books that build on these books, but I like some of the tidbits that happen in the book, that are in the book, like this one. So this is the rat hole picture that is in this book. It's actually, maybe, let me see how much time we have. Okay, I'm going to go through this relatively quickly. But the person who wrote this book, Raj Jain, says that even if the performance analysis is correctly done and presented, it may not be enough to persuade your audience, the decision makers, to follow your recommendations. And this is actually very good advice in general. Nothing to do with engineering or science. Again, if you're in business, you're going to present something to someone, and people are going to poke holes at it, especially the decision maker who cares about the bottom line, right? And the list shown in box 10.2 is a compilation of reasons for rejection heard at various performance analysis presentations, as we will see in the next slide. You can use the list by presenting it immediately and pointing out that the reason for rejection is not new and the analysis deserves more consideration. Also, the list is helpful in getting the competing proposals rejected. So you can actually use this for gaining an advantage. So, and it goes on saying there's no clear end of an analysis. Any analysis can be rejected simply on the grounds that, okay, this is not working. The problem needs more analysis. This is the first reason listed in the next box. The second most common reason for rejection of an analysis and for endless debate is the workload. Since workloads are always based on the past measurements, their applicability to the current or future environment can always be questioned, and you can always think about new workloads clearly. Actually, workload is one of the 4 areas of discussion that lead to a performance presentation into an endless debate. These rat holes and their relative size in terms of time consumed are shown in this figure over here. And presenting this cartoon at the beginning of a presentation helps to avoid these areas. I think this is actually nice advice. Okay, and this is actually really interesting. Some of these are actually, as I mentioned to your question, some of these are actually old in terms of terminology, but you can actually translate it to what it is. But you can see that these are reasons for not accepting the results of an analysis. First one is this needs more analysis. The second one, you need a better understanding of the workload. I like this. I like some of these last ones over here. 24 is that's beyond today's technology. That's not a good attitude in research. 26 is why change? It's working okay. That's a terrible mindset, basically. This is not the mindset that a researcher should have. But you see that this happens actually whenever you publish or try to publish papers. Especially if your idea is very out of the box, it becomes very difficult to get it accepted sometimes because people are so, the existing technology and the way it works is so ingrained in the thinking of people that they cannot really take the leap and go out of the box and accept a different way of thinking easily. So this is actually important for whatever you do in life. Whenever you're presenting an idea, you will be challenged this way. Okay, I have some advice on talks. Actually, I borrowed this from my colleague Kayvon Fatalian, and I would recommend actually downloading this PDF and going through it. There are many useful and simple principles in terms of how to deliver talks, and I agree with most of them. Maybe not all, but I'm not going to go through every single one and say which one I agree, which one I disagree. Most of them you can assume that I agree. But this, you can see some of them over here that are copied and pasted. Every sentence matters, so everything you put matters. This is also good advice for writing papers, by the way. The audience prefers not to think. Basically, about things you can just tell them. Basically, make it so smooth that the audience, it flows so nicely, right? Don't make people think. Surprises are bad. Say why before what. And this is very important, actually. I read a lot of papers, and a lot of papers just give me what they're doing, but they don't tell me first, motivate why they're doing it. And that why is extremely important because it sets the context for me to understand what is happening afterwards, right? If I have no context, I read and read and read, and I get lost. But I have some context, then I can actually tie what they're doing over here to why they're doing it. So giving those goals, higher level goals and higher level ideas is really important first, and then you go into the lower level mechanisms. And explain every figure, graph, or equation. This is important. Don't be like some industry where they don't have any access labels, for example, and they have some chart. That happens. I'm not going to name companies, but most companies are guilty of that. For a good reason, I guess. If you're in industry, you may not want to reveal everything that you have. And when improving the talk, the audience is always right. This is also good to keep in mind. Okay, I'll give you some examples also inspired by Kayvon's. Do you know who painted this painting? Yes?
DALI.
DALI, okay, that's good. There's a side channel over here, but I don't think you use that side channel when you answer the question. Meaning it's already written over there. So this is Salvador Dali's painting. And you wouldn't associate Salvador Dali with this painting, assuming you know what Salvador Dali is famous for, right? But he did paint this one when he was young. Okay? And then he learned how to paint. What about this painting? Who painted this painting? Anybody?
DALI.
Also Dali, exactly, yes. Now he figured out the principles, he broke everything. Right? And he figured out how to break them also. That's 1937. So what's my point? Basically my takeaway, especially for people who are just starting research and everything, is first, learn the basic principle before you consciously choose how to break them. So doing the those basic principles, doing those basic paintings, enable you to actually figure out how to break them in the best ways. And I think this is a very good principle. So keep this in mind. So once you, if you want to break some of the principles in terms of presentation, be very careful. I'm not saying don't do it, but be very careful, because once you go out of the way, it may be very difficult to present things in an easy to understand way. And again, I think writing is very important, very similar to this. Whenever you write something, it's always good to, especially if you're doing creative writing, for example, it's always good to be very grounded on relatively simple writing and not so fantastical writing to begin with. And a lot of the writers who are famous for fantastical writing actually did something similar to what Dali did. Okay, how to participate? Very quickly, hopefully you come prepared, read and critically evaluate the paper. That's my hope for everyone, but I understand that it's not easy to enforce. Think new ideas if it's possible, bring discussion points and questions, read other papers, be critical. Even if you don't do any of this, follow the discussion, follow the presentation really well and be critical. And maybe develop ideas while you're doing it. Paying attention and discussing and contributing is important. And participate online before and after each meeting. Let me give you an algorithm of what we're going to follow. Basically, we will assign presentation dates, and once you know your paper, you will start preparing for it, hopefully, and start early. Read the paper carefully, read it critically, read it creatively, think of improvements. Try examples by hand if it's possible, try tools if available. Of course, this depends on how much time you want to spend. You don't have to do all of this, but if you're really excited about it, you can do it. And consult with your TA or mentor if you have questions. And then you create a draft presentation. And of course, that presentation is important. You can read this on your own. Focus on the key concept. Do not present all the details. Clearly, we don't have time to present all the details. So the outline that I showed you earlier was good. And then you need to prepare for the meeting. And this is the most important part, perhaps. You will basically need to schedule meetings. You need to send the slides in advance and write down some questions that you may have. And make sure you address the feedback after the meeting with your mentors. And there are two meetings, and meetings are mandatory, and they should happen at least 1 week before the talk. Don't leave it to the last minute, because your mentors may not be available in the last minute, and then if you don't get feedback, then your presentation may not be as good as it could be, basically. And I think this sort of iteration actually improves the presentations, and a lot of people who've taken this course in the past said that those meetings with the mentors have been extremely useful. Okay, so let me cover this one too, and then we will be done. Okay, so basically this is the grading rubric. We can cover this later on. Basically, quality of your presentation, quality of this final synthesis paper, and attendance. Participation is a bonus, so if you really want to increase your grade, participation is good, but I think participation is good for making the best out of this course. And hopefully you're not here for the grades, because it's just a seminar course anyway, right? It's just 2 points. Is that true? Yes. So hopefully you're here to make the best out of the course. And clearly the quality has several questions, and you can read this again. These slides will be online. Okay, so feedback is important. We'll try to briefly discuss strengths and weaknesses of your talk in class. If you prefer us not to do this, please let us know. Maybe we should do this more, because I always get the feedback that we don't do this enough, because usually what happens is presentation runs long and we have a lot of discussion and there's no time for me to give feedback to the presenter. But if you prefer that, please let us know also. But if you don't prefer that, please let us know as well. And you can of course arrange a meeting with your TA or myself to get feedback as well. So we will have an expected schedule. we will meet once a week with two presentations per session, assuming we remain at 22 people. If some people drop, then we will have fewer sessions. And if you're not registered, has everyone registered for the course? Okay, so there's no people, there's no person here who is not registered for the course. Okay, then we don't need to discuss it. Basically, each presentation is 50 minutes, including questions and discussion. And as I said, paper assignments, we will do it online, study the list of papers, and we will send email about what you will do to select the papers and how you will select the papers and rank the papers in terms of your interest. And before I conclude, I will remind you that there is a homework that is due soon. Please submit it. And paper review preferences, check your email and the website for instructions, because you will need to do this soon so that we can schedule all the presentations over the semester. And I think that concludes the first session. Any questions? Yes?
What is if you can't attend the meeting or something?
So then please let us know early. So if you have a constraint, for example, that you know that you definitely cannot come that particular date, please let us know by email so that we don't assign you for that date. And you should also let us know so that we take that into account in terms of participation. But please try to minimize the number of meetings. Yes?
Are we required to bring our own laptop or whatever for the presentation?
That's the best case, basically. But if you need a laptop to present, please let us know again beforehand so that we can prepare for it. But your laptop is probably the best thing because you know the quirks of it. Whenever I am forced to present in some other laptop, I always push back and say, I don't want to do that. Because even if my laptop is not reliable, I know when and why it's not reliable. But I have no idea what some other random laptop would do. Because usually I use PowerPoint and there's animations, and when I plug it into some other laptop that doesn't have the right PowerPoint model, all the animations go, yeah, odd. But let us know if you need a laptop, for sure. Okay, any other questions? Okay, well, we're done with the first session then. Next week we're going to give an example paper review and discussion. And see you next week.